Hey kittens, welcome back to episode 2 of Quantum Cast, and we're back with more science STEM facts for you to enjoy. So,
Yeah, that's great.
welcome back.
Do we?
Quittens means quantum kittens. Okay, go on.
Okay. Geneva.
We're gonna start off with a quick recap about our recent trip to Switzerland. We went to Geneva to visit CERN, and yeah. Do you guys wanna start off, Amy?
Yeah, so we went to the United Nations office first, and it was just after we got off the plane, so it was very tiring and everyone was falling asleep. But it was interesting somewhat. Especially when like the tall person started talking about like aliens or stuff. I don't know about you
Oh.
guys.
No,
But
We
she
had a
said
good
it
tour
like
guide.
that.
We had a good tour
We
guide.
did.
The
I
best.
loved her.
What,
Yeah.
Chanel?
Chanel.
Chanel.
Shout out to Chanel. Where were you?
Yeah, so that was interesting, and it was a very pretty place. So yeah.
What happened on day 2?
Set. You know what? I was so disappointed with it because I thought we'd actually go and see the Large Hadron Collider. I mean, it was nice. It was definitely nice. It was definitely interesting. And oh my god, there were like, of course, Switzerland, but like there were lots of like Italian people, and there was like, and I interacted with a few, and like there was this guy that like was explaining in Italian. I think something about informatics and physics and how it relates to it, and quantum physics, and also 2025 year of quantum physics.
Yeah.
So we love that. And he was explaining it so well. I was enhanced. And then I told my physics teacher about it, and then he was like, maybe I should start talking in Italian, but whatever.
What else? We played a lot of cards.
Yeah. Lots of bullshit.
That's all I have to say.
All you have to say.
But yeah, we got to see Lake Geneva and like the jet. We got to go really close up to the jetty, and we went to a Swiss restaurant as well. That was good. And then we went bowling as well. We had like fun little activities. We got lots of free time, and we took the first day we had free time. Like on the second day, we took a random bus and just got lost and we used our public transport cards. Like we had free public transport. We used it so well.
Yeah.
So well. Like the teachers, that was money spent well. But yeah, that's our little trip to Geneva, and
It was great.
it's good. It's good.
Enjoyed it. Today I'm going to talk about whether the theory of everything is possible in physics, especially with our current understanding. So the theory of everything is like defined as the holy grail in physics, and is looking to unite the two pillars of physics, namely general relativity, Einstein's general relativity, and quantum mechanics. Also, it's essential to note that whilst we are looking for this theory to be the base of the universe, the foundation of the knowledge of the universe, it's not endpoint for the research. Also, not every scientist necessarily believes this is like a useful endeavor. Some believe this to be futile research because they believe that universe law would not unify in a single theory. So what's our current understanding? Our current understanding of physics is in the Standard Model of Particle Physics, which delineates the subatomic world and the 3 out of 4 forces. So it has the electromagnetic force, which intertwines electricity and magnetism, and it holds atoms and molecules together through interaction of the electrical charge components of it. The weak force, which is cause for radioactive decay, and the strong nuclear force, which holds subatomic particles together to make larger subatomic particles. So whilst it's a very supportive theory of what we have right now, it still has some limitations. So scientists have discovered that neutrinos have a mass, which is important.
What that made you laugh?
Yeah.
It kind of sounds like Italian for neutrons.
Oh, to be fair, I think it does come from like Italian, because in Italian we add ino to things that are small. And I think it did come-
Lovelino.
yeah, literally. I think it did come from the Italian. I think Neil deGrasse Tyson was talking about it, but I don't quite remember in what video, so probably have to search that up. So yeah, those were supposed to be massless according to the standard module of particle physics. Italian neutrinos, yeah, but they have a mass. Also, it doesn't account for most part of the universe, since only 5% of the universe is composed of matter that we know, and 95% is composed from dark matter, which we think it affects the shape of the cosmos, and dark energy, which is predicted to be the reason for the acceleration of the expansion of the universe. So it doesn't account for that. And
dark energy.
yeah,
Do you mean it in like a scientific way?
Or I don't mean it in a spiritual way. Not that like 95% of the universe is composed of some spiritual sort.
So like with dark energy, like does it have like a form?
That's what we don't know. It's everywhere, but like we're unable to detect it.
So it's not harmful.
No, well, it composes 95% of the universe, so I suppose it's not.
Wait, so this might be a dumb question, but so there's dark
No question is
energy.
dumb question.
I know, but so is the dark energy around us right now? Like,
Yeah, well, now it sounds like a spiritual way, but yeah.
as in, like, what characterizes dark energy? Like, I've heard that it's basically what makes up the universe, but what sort of? Oh, sorry, there's a fly that came. Yeah, what composes? Well, you know what? How do you define it?
We still don't know. That's the thing. I mean, there are predictions that like axioms would be particles that compose of dark energy, but it's all theory at this point. We don't really have concrete proof of dark energy or dark matter.
So how do you know it's dark energy, not normal energy?
Because normal energy you see around is form as kinetic energy or elastic energy.
Okay. that
You're
makes
able to detect energy, yeah. So, and also, scientists suppose that antimatter would be formed alongside matter at the beginning of the Big Bang. But because matter is all around us, it means there was majority of matter, which just contradicts what the laws of physics would be in theory. So it also, more importantly, where I'm getting at, it fails to account for the fourth force, which is the weakest force, but it's gravity. So it fails to account for that, and it hypothesized the existence of a graviton, which is a hypothetical elementary particle that, like, let me find it. Oh, the definition is the hypothetical elementary particle that mediates the force of gravitational interaction. So it's a good theory that we have, but it doesn't connect, the two pillars of physics. And why is it so hard to unify those? So both discovered in 20th century, they contradict each other in fundamental ways. While general relativity expresses gravity as a curvature of space-time rather than a force, so it works great as an explanation for large bodies in the universe, so like black holes and planets and stars. And then quantum mechanics describe nature at a subatomic scale through probabilities and wave functions. However, it doesn't incorporate the wrap
Of what?
of fabric.
Okay.
And also, whenever scientists have tried to apply general relativity to quantum mechanics, they have found infinities, which great in maths, but they don't tell us much in physics. So that's
They're useless.
Yeah, so we're just not getting concrete answers. For example, we have the information paradox, which is if information falls into a black hole, according to general relativity, it would be destroyed, and then the black hole would evaporate, and then Hawking radiation would be released, so like thermal radiation. Yeah. However, according to the laws of quantum mechanics, this information cannot be destroyed, or it cannot disappear. And quantum information is demanded to be preserved forever, so it should be possible to trace the universe forwards and backwards.
So where does a black hole go?
What do you mean?
Wait, so once the information goes inside the black hole,
Yeah, according to general relativity, it should be destroyed.
as in the black hole's destroyed with it, and the
No,
information.
no, the information. Because of the singularities that are in the black hole, the force is so strong. You know, spaghettification and stuff. Spaghettification, like
Spaghetti.
you become like a spaghetti. That's how I would like to die, in a black hole. I don't think that's gonna be possible, but yeah, that's about it. Oh, okay. So how do we unite these? Our base is supposed to be quantum gravity. And quantum gravity is expected to describe space and time at a Planck scale. I don't know what a Planck scale is like. The fundamental limits of where physical laws stop working. It's like the smallest. It's like the Planck length, which is the
Oh yeah,
smallest
yeah, I
length,
get. Okay.
and Planck time. So we need to do further research, but we do have some candidates for the theory of everything, which is so exciting. String theory. Love string theory. That's a theoretical framework in which assumes that particles are made of strings and they have different tensions and they vibrate in different ways. So like there are different particles like photons, electrons, and all the particles that are in the standard model and some more. So why is it good? So it predicts the existence of axions, which is a particle believed to be dark matter. So it accounts for 95% in theory. Also, why is the standard model interaction with local? So like the photoelectric effect. So when you shine UV light on a metal surface, well, at a certain frequency, at the threshold frequency, those electrons will then emit photons. Okay. And that's quick, that's immediate, right? Because according to the particle model of photons. However, with string theory, the particles are emitted gradually. Which also gets rid of the infinities that come up with the standard model. Also, it accounts for supersymmetry, so it predicts that fermions and bosons are equal, which could explain dark matter and solve the hierarchical problem. So the hierarchical problem is like problem concerning the large discrepancy between the weak force and gravity, because the weak force is 10 to the power 24 times stronger than gravity. And we all know that string theory accounts for more dimension than the four we have, 3 for space and 1 for time. So we need.
I'm so sorry. Isn't string theory the one that says there's 11 dimensions?
Yes.
Yeah, 11 dimensions. I remember hearing a podcast about. Yeah.
I love that. So yeah, it does have 11 dimensions. So 7 of them are curled up. And because it has 11 dimensions, and because the strings can vibrate in so many ways, it also comes with a multiverse theory, the theory that like every set of vibration then composes like this different universe. And also according to Tegmark, he says that if a structure can describe mathematically, then it definitely exists.
Yeah. You know how you mentioned that they're curved up? What do you mean by that?
They're curled up. So like, okay, if you see an ant on a straw. So you have a straw and you see the ant, and it's just a bit far away. You just see the ant moving in 2 dimensions. So it goes that way or it goes that way. But then if you get closer, there's like 3 dimensions. And just because the ant is so small, you're so far away, you see 2 dimensions, even though there are 3 dimensions, and the ant sees 3. So those are like really small, and there are like multiple ways in which those 11 dimensions can be curled up.
By curled, do you mean like physically curled up, like?
Wait, wouldn't it be curled up for the outside perspective, but it wouldn't be curled up if you're in it? Is that what it means?
It's more, but curled up might not be the greatest verb to describe it, but I think it's close to it, because you're just unable to. I mean, we are unable to see those 11 dimensions if they do exist, but string theory only works with 11 dimensions. That's
Because
why
is
we
it related to Amy's topic? You know, with like the crochet, like with the curves.
Yeah.
Is it related to that?
I'm not quite sure. I think yeah. Well,
Wait. So where do the 11 dimensions exist? Like, is that
that's a great question. I wish I knew.
okay? Fair enough.
No, but I don't know. I was listening before coming here. I was listening to Alex O'Connor,
Shout out to Alex O'Connor.
greatest love of my life, and Brian Green talk about it, and like it's just even I got confused while listening to them because it's just this theoretical framework that we use, but like we're not able to find those 11 dimensions. Well, there's 7 more dimensions, so I'm not quite sure where those dimensions are. I wish I knew. I do. It's yeah. Sorry about that.
No, it's fine.
And last but not least, no, it is quite least because I don't quite like this theory. It's the loop quantum gravity, which is second candidate for the theory of everything, and it tries to quantize general relativity. So it tries to reformulate Einstein general relativity under a quantum lens, and whereas when uniting the 2 pillars of physics, we encounter singularities when gravity. What the hell? When gravities are the strongest, like in a black hole, so like the singularities. In this theory, we can get rid of them and replace with ultra dense matter. And it also predicts Hawking radiation. So like the whole information paradox makes more sense under loop quantum gravity, but it doesn't solve the problem time. Also, I just don't like it. I just genuinely don't. I think string theory is just more. It's nicer. And yeah, so this will. Well, this is it. I think I think the theory of everything is a clear possibility in the future with more advanced universe, and it possibly will be a reality in the future. Hopefully, it will be string theory, but I haven't got around to it yet. I started it, but the books by Brian Greene, I think, The Elegant Universe and The Fabric of the Cosmos. I started reading both of them, but they talk. Especially the Elegant Universe, it talks greatly about string theory and this topic basically. So if you find it interesting, you should probably go and check that out. And yeah, that's about it. That's string. Any questions? No. That's great, guys.
Hi everybody. Today I'm going to be talking about cell reprogramming and coding. And it's about something strange that's happening inside our body right now. Every cell that we have, every skin cells, every skin cell, brain cell, blood cell, it basically carries the instruction to make every single enzyme, every single protein, or every single chemical you could possibly need. But somehow most of them don't use all the instructions they have and only use a tiny part of those instructions. And the questions I'm asking today and answering today are why? Why is that? And what could happen if we learned how to unlock their full potential? So, imagine if every building in the city had the blueprints to become a hospital, a restaurant, a school, whatever, but only a few of them did. And that's exactly what's happening inside our bodies right now. Every single cell from our brain to our bones, they carry the full set of genetic instructions to turn into to make every enzyme, every protein. And if you take insulin, for example, it's a hormone that's essential for regulating blood pressure, and it's only made in the pancreas. But somehow, every cell in our body has the genetic code to produce pancreas. And so yeah, your neurons or your liver cells, they could all make insulin, they just don't. And it's because something in them is keeping the DNA silent. And the silent control system is gene regulation, which is a complex web of switches, signals, and chemical modifications that decide which part of a cell's genetic code should be switched on or which part should be switched off. And And scientists are asking questions such as, could you force a cell to do something it normally wouldn't and reprogram it or even reset it completely? So, in 2006, a Japanese scientist named Shinya Yamanaka, sorry if I butchered it, Yamanaka figured out how to. He was studying stem cells, and which are basically the master cells in embryos that can become anything from brain cells to heart cells to liver cells. And thing is, working with embryo cells is quite ethically controversial because it's like, should you use something that could have technically been life? But yeah, he asked a radical question of, could you take a normal adult cell and like a skin cell, for example, and turn it back, reverse it back to becoming a stem cell? And it turned out you could by just adding 4 specific genes, which are also known as the Yamanaka factors, because he came up with it, so he has to name it. Okay, they're called OCT4, SOX2, which is SOX, not SOX, KLF4, and then C-MYC. And these 4 factors, if you introduce them to an adult cell, it could reset the cell's whole identity. It would strip away the markers and anything that made it specialized. And the cell would then become what's called an induced pluripotent stem cell, or iPSC, which is basically a biological blank state. And this discovery was so powerful that Yamanaka then ended up winning a Nobel Prize for Medicine and Physiology in 2012. And it basically changed how we think about cells and the way that they could be programmed. And then, he's not gone. This whole research hasn't gone too far in because of like the lack of funding we have and the ethical concerns that we get because of this. But scientists such as Derek Rossi.
Daniel is crying right now.
sorry, Derek. Derek Rossi, who would later co-found with, Moderna. He built onto Yamanaka's research, and he began to push the idea even further. His thought, instead of permanently changing the DNA, his idea was to use mRNA, which is a molecule that temporarily tells cells what to do. So in his model, you wouldn't need to edit a cell's whole hard drive. You could just send a quick text message, get the cell to produce a protein, and then the instructions would disappear after a while. So it would turn into a blank state. And this approach, go on.
How are you sending those messages?
Through the body?
Yeah. Through WhatsApp?
Through WhatsApp, through Snapchat.
Through WhatsApp, what if they leave it undelivered?
So you would use mRNA because they go they go into the cytoplasm, right? Yeah, they go from the nucleus to the cytoplasm, and then they basically construct protein. They do protein synthesis. So then you would get these mRNA molecules to go around sending these cells what to do, tell them what to do.
Yeah.
So it'd be like just basically going from one cell to another cell, like a message.
Oh, okay.
And that's how you'd get them. But yeah, this research exploded during COVID-19, the pandemic, because we were using mRNA vaccines. But its actual potential, it reaches so far beyond infectious diseases, because it's about controlling biology with messages and not surgeries. It's basically like sending a message to a damaged patch. A damaged patch. Tissue.
So technical problem. Yeah. Do you want to continue?
Okay, it's basically, imagine sending a message to a patch of damaged heart tissues. Stop looking.
No, I was looking if it was gone.
Is he gone?
He's gone.
Yeah. I didn't understand. Oh, sorry. I didn't understand at first what was going on. I was looking if Amy was looking, but she wasn't. What the hell were you looking at? Because I was looking at Chahat and he came direct into
Technical issues, cut this part out. Sending messages to damaged heart tissues, and then telling them to rewire themselves and reprogram themselves after a heart attack, and having the message delete itself after the job is done. So that basically eliminates the need of surgeries.
Why do you need to delete the message?
Because if it stays, it'd be like junk afterwards. You wouldn't need it. It'd just be taking up extra space. Like, you wouldn't get. It would just. reprogram itself to just combust, maybe to finish off.
Wait, so you're destroying information,
Basically, because it would be like,
but you cannot destroy it or create mass. So where is it actually going? Or are you taking out your bodies on form of pee or poo?
what? What? Who's that?
Are you like peeing it out? Guys, I don't do biology.
No. Okay. I think.
Would it just like change the type of cell it is?
I think it would.
Yeah, but it still has that information.
Right.
It has a lot.
It would delete. It would delete. It's like, you know how we've gone through evolution.
Have we? Some of us haven't.
Well, most of us have gone through evolution, and how a lot of like the information that we used to hold has just kind of been stored away into a junk pile. Like, oh yeah, okay. My biology teacher was telling us that we do have all the information, ever since we've become whatever we were before, right? But it's just deleted. It's just kept. Is it what, introns? Would they become into introns?
Wait, is it?
Like, we do have it all, but it's just junk DNA.
You know when like you send the message for it to become like a heart cell or something, and that information is spliced in to form the mRNA,
Yeah.
and then after that's happened,
It would splice again.
Yeah.
Yeah.
It would be taken out.
It'll be
'cause we've
taken
got
out.
No need for that.
It'll just be taken. Where do introns go?
Introns are spliced out, and I think they're just in the cell. Like,
They're still in there, but because they don't code for introns, basically are non-coding DNA. Genes that don't code for DNA don't, and then exons code for the DNA. So they're spliced right into the process of like when you're doing translation and transcription, and they're still there, but they don't code for anything. So I think that's what it means when it says that it would delete itself. It would become useless.
Or could they be used in another DNA sequence where this time it is useful?
But where would you use such specific cells?
No, but like, you know, like the intron sequence that's out, it won't be part. So like, it won't be like the sequence that codes for like a heart cell, because once it's removed, it could code for something else if you like, insert it back in somewhere else.
Oh, so reprogram into something different. Is that what you mean?
Maybe.
Because
I doubt it's just gonna like sit at the bottom.
I think maybe. I'm not entirely sure. Don't quote me on this, because this is just what I've taken from whatever I could find. But maybe.
Not a maybe.
Still a maybe. I'm so sorry I can't answer the full question, but I think my best bet would be that they become non-coding DNA, unless they're like rechanged to become something that's useful. Yeah, that's what I think would happen. But yeah, so labs around the world, such as the MIT Synthetic Biology Center or the WIS Harvard Institute at Harvard, or research groups such as in Germany, Japan, China, they're still experimenting with reprogrammable cells. So cells that can be designed to recognize a cancer cell and destroy it, or rebuild a damaged tissue group, or even act like tiny sensors floating around in the bloodstream to like see if there's anything that shouldn't be there. But it's not all science fiction. There are serious challenges to this, and these are challenges as to why we've stopped. We haven't progressed so far with our research. One of the biggest problem is that one of the 4 Yamanaka factors, the CMYC, is actually associated with cancer cells, and it's known as oncogene, a gene that when you activate in the wrong context, it can cause cells to grow uncontrollably, so basically differentiate into a cancer cell. And if you try to reset it too aggressively, it can turn into dangerous. It can have dangerous. It can have dangerous cancerous behaviors. And then another risk is having genomic instability. And that's basically when you rewind a cell, you sometimes introduce mutations or errors that can cause it to, well, mess up your whole body, right? And if this was in a lab dish, it wouldn't matter. But are you really willing to take the risk in a whole organ system, or like a whole organ? It's like, yeah. So where do you draw the line, I guess? it would basically just be like test rats, lab rats, to see if like it would work or not. But there are also some practical limitations. So if you turn an adult cell into an iPSC SC, yeah. In the lab, it's inefficient, it's slow, it takes extensive chemicals, it takes lots of time and lots of careful monitoring. And if you were to scale that up to just a whole organ or a whole person itself, it's like, how can you do that with it still being reliable and safe and guaranteeing that the person will exist in like 5 years to come? Because if they die of cancer.
Yeah,
Yeah.
that's a nice way to say
But yeah, also, if we still were able to reprogram them, we still have our immune system. And it's like, because our immune system is so good at detecting when something shouldn't be there, and like killing it and destroying it with through like white blood cells and whatever. And if you have even a small difference between a host cell and a donor cell, something that we wouldn't be able to even tell, the immune system will, and then it most likely will end up like, destroying it. And yeah, so those are the risks and like possible limitations. But even despite this, we still are making progress with this all. Some labs and some teams, they're making universal donor cells, which is basically the cells will be edited to be invisible to the immune system, and by removing like certain surface protein cells. And some will have this feature where they can self-destruct, and others are designing self-destruct switches that could kill off modified cells that have gone rogue. And what?
someone's dying in the background.
Yeah. But yeah, there's people like David Sinclair at Harvard that are still using Yamanaka's factors to reverse aging in cells. So where without turning them into stem cells in the middle, so they'll just go from being one specific cell to another specific cell that they need it to without using stem cells as like a midpoint. And their idea is to rejuvenate cells without actually having to reverse its whole identity and causing mutations or like whatever. And we are still in the early days of this. It is still a very amateur and beginner level. Well, not beginner. Okay, maybe I shouldn't diss the scientists. Not beginner level.
I believe it just is a Nobel Prize winner.
Sorry, but it's still quite. Oh my god! Someone dying in the back. It's still quite in its beginning stages compared to like how far we've gone with other research, right? And we do know that every cell has the power to do anything. It's just like figuring out how do you get it to do that, and we just need to believe in them. That's it. But it's saying that maybe the future of medicine isn't about building new technologies from scratch. Maybe it's about learning how to speak the language that every cell already understands. And that's it. That's my little rant about cell programming. So yeah, thank you for that. Oh yeah.
Wait, how would you skip the midpoint?
So, because you'd be able to reverse them in aging, in terms of like you'd be able to program them so they're going back in time to the point where like they go back in time, but not so back in time that they go back to being stem cells. Because they'll start off as stem cells, and then differentiate, but they'd be able to precisely monitor it so it goes back enough, but not enough to become a fully fledged stem cell.
But won't it still have some of its old features?
Yeah, exactly. That's basically what we want. We're still changing it without losing its original identity.
Why would you want the old features as well?
I mean, because if you were to go back all the way to stem cells, and they go from stem cells all the way to a new cell, there's so much time for it to go wrong. So it's keeping it as a precaution to not go all the way back, but it's at the point where it's like just starting to form.
Wait, so say it was like a heart cell originally,
Yeah.
and then you want to turn it into like a liver cell,
Yeah.
and then you go back, and then you go forward a lot.
Yeah.
So it has switches for both heart and liver.
I think it would have some parts of the switches for heart cells, but not enough for it to become a heart cell.
So it won't interfere with its new function.
No, I don't know. I'm imagining it won't. Otherwise, that's a big. Because then you have like hybrid between a heart cell and a liver cell, don't you? I think, yeah. But that's it. Thank you.
So today I'm going to be talking about Fermat's last theorem, which is it was the most prized puzzle in all of pure mathematics for 358 years until it was solved 30, 32 years ago. A proof was found. So yeah, it was the most famous puzzle, and I'm going to talk about that today. So Pierre de Fermat was born in 1601 in southwest France, and he wasn't. His family pressured him to have a career in the French civil service, so he just studied maths as a hobby. So he studied the Arithmetica, which is an ancient Greek maths text, and he made lots of maths notes in the margins, and like he made lots of conjectures which are like unproven theorems. And the thing is about Fermat was that he liked to gatekeep, so he'd have like a lot of like great proofs of like these really difficult problems, but he'd never share them. Like he'd tease other mathematicians that he had the proof, but he would never share them.
Wait, so he didn't know that he would still get credited for it?
He didn't really care about credit. Like
He was just doing it for the pleasure.
yeah, he just liked to be the only one with the knowledge.
That's so crazy.
Yeah.
That's the level I aspire to. That's crazy.
What evilness?
Not
Yeah.
evilness, but I would share, of course.
So, yeah, a lot of his conjectures that he wrote in like the margins of his copy of Arithmetica, a lot of proofs were found like later on by mathematicians, except for one that he said. So this is his last theorem, and he said that he found the most marvelous proof for it, but the margins were too small for him to write it in. So the proof died with him, and no one ever knew what it was.
That's the most ridiculous thing I've ever heard.
Yeah, it's a bit silly, but and to this day, no one knows what the proof was, because while the proof that has been found now, it's so advanced that he would never be able to find out in that time. So yeah.
You know, when you say margin, do you mean like?
Yeah,
But why is he writing it in like margin?
Yeah.
I don't know, it's just
Was it 3/4 to a fold? Maybe it's quirky.
no, he just like took notes in it.
Mathematician.
So he just gave up because he didn't have space.
No, he did have a proof, or at least he said he did, but he never wrote it down. Exactly. So some people say like oh, maybe he didn't have a proof, but yeah, he said that he had a proof and he could prove it. So it was known as Fermat's last theorem, and basically it came from when he was reading about Pythagoras in the Arithmetica, which is a squared plus b squared equals c squared. So there was in the Arithmetica there was proof of infinite Pythagorean triples, which are like whole numbers that fit into the equation, Pythagoras' theorem. So the proof of that is, so think of the square numbers from like, so you got 1, 4, 9, 16, 25, and the difference between all those square numbers is it's an odd number, so it increases the same amount each time. So the difference between all the square numbers, it goes 3, 5, 7, 9, and so on. For all the square numbers, it repeats in the same pattern. So to find a Pythagorean triple, you just like go to the difference, which is a square number. So 9 is one of the odd numbers, and it's a square. It's 3 squared. So it's also the difference between 16 and 25. So basically, a Pythagorean triple is 3 squared plus 4 squared equals 5 squared.
Okay.
So yeah, and it happens later on. You've got 12 squared plus 5 squared is 13 squared, I'm pretty sure, yeah. So it's just whole numbers that fit into that equation. Fermat, though, he was thinking, what if instead of a squared plus b squared? What if it was a cubed plus b cubed equals c cubed? Or a to the 4 plus b to the 4 equals c to the 4, yeah?
Why is that relevant to our knowledge?
No, he was just...
Is that useful at all?
Okay, honestly, it's not. it's not, but the thing is, it... it wasn't. He was just curious, and I don't know why mathematicians for centuries were so stuck on this this puzzle. It's not important at all, really.
So why did
But-
nowadays mathematicians still found a solution to this last theorem? Like, all men do is lie, right? so anyway, he might have not had the solution, but then we could have been like, yeah, sure, whatever, and then moved on with our lives. But they actually put effort to find it, didn't they?
I mean, I don't know. I guess with the more mathematicians that tried, it became more of a like, oh wow, so many great mathematicians can't do this. I want to give it a go.
Right.
And it's just like with pure maths, it's less of like pure maths and number theory it's useful in cryptography, so like code cracking and stuff. But so a quote from the person who actually who actually found proof for it, he said like that pure mathematicians, they just love challenges, like they just love doing puzzles. So I guess that's what it was.
All right. Okay.
So yeah, the proof died with Fermat, and so Euler in 1707. Oh yeah.
Do you know how old Fermat was when he died?
No.
It's just interesting. It just came up in my head.
No.
No,
I
okay.
don't know, sorry.
That's okay. I'll search it up.
So in 1707, Euler was born, and he was another very gifted mathematician, and he did a lot of work on like prime numbers and calculus and algorithms.
Wait,
Yeah.
what is the last theorem?
Oh, yeah, I forgot to say that. Fermat's last theorem is that a to the power of n plus b to the power of n equals c to the power of n. That there will be no solutions for any power of n greater than 2. So
this only goes up to 2.
So you can get a squared plus b squared equals c squared, and you'll get whole numbers such as 3, 4, and 5 that fit into that. But you won't get any other whole numbers solutions for a, b, and c if n is 3, 4, 5, or anything bigger than 2. So
But what if n is infinity? Then it would work, right? Or if n is 0? Well, yeah, if n is 0.
n is 0.
Because
No,
then you
because
have-
then the 1.
Yeah, then you have 1 plus 1 equals 1. But then infinity would work, right?
Infinity. The thing is, like, it's just any number bigger than 2. So the proof is like for n equals 3 all the way to infinity. Like,
But why wouldn't it work for infinity? Because there are different sizes of infinity, but I guess like it makes sense for it to work.
I mean, I guess like the thing is like the proof is that it doesn't work for any of the biggest number you can think of. It wouldn't work for, so it wouldn't work for infinity either.
So what proof did he use?
Fermat.
Fermat. Yeah.
We don't know.
I mean, it can be used proof by exhaustion. Or...
I mean,
Imagine if he used
no, because that wouldn't work.
no, of course not.
Because actually later, like when computers were more advanced in like the 20th century, they did try using proof by exhaustion, but they did prove it for like a billion different numbers, but that's never going to be like an actual proof, because what if it works for 1,000,000,001? So
Yeah.
or 1,000,000,001. So you need a proof that works for every single number all the way to infinity. So yeah.
Wait, I was gonna ask, so what, his proof, what would you use it for?
Like besides the theorem, it's really like
It's like very niche.
yeah,
if it
it
only
is.
works up until 2.
Wait,
no,
what?
it makes sense for it to work till 2 because you have the 2 squares and then the area equals of the Pythagoras theorem.
Yeah.
It makes sense for a Pythagoras theorem to work. But then, like, I think if n equals 3, then it would get into 3D. But I don't think it works for like.
Yeah, I
3D.
was thinking. I mean, the proof is that it doesn't. Fermat's saying that you won't find any whole numbers. It wouldn't work for any whole numbers if the power is greater than 2.
And we're using it in terms of like a triangle.
I mean, not really, because when you get to like higher powers than 2, it doesn't look like a triangle anymore, I guess.
Does then like n equal to the number of dimensions? Because you have n
Yeah.
equals 3. Yeah.
Yeah.
So it'd be hard to have.
But I guess they didn't really think about like dimensions. I guess he just thought about like just on a piece of paper what it looks like.
Yeah.
I mean, I don't think it would be 2D if you imagined it, because higher than 2, like if you had if it was a cube, then it would kind of look like I don't know, 3D Pythagoras. I don't know. Yeah, it was okay.
Sorry.
It's okay. It's okay. It's a cute caterpillar.
Find out a caterpillar and put it on the jeans. No. Okay.
So
Are you sure that's the caterpillar?
Yeah. Okay.
okay, so back to Euler in 1707. He tried to work on Fermat's theorem and find a proof.
Amy, get it.
Okay, great. So he tried to prove that if he could prove it for one case of n, then maybe he could use that to prove the theorem for every case of n. So when in the margins, Fermat he used infinite descent to prove the theorem for n equals 4. So he proved that if n equals 4, there are no solutions. So basically, infinite descent so a to the power 4 plus b to the power 4 equals c to the power 4. And by examining the properties of those numbers, of a, b, and c, it meant that you could make it smaller, that you could find a smaller values and make the equation smaller. And you could keep doing that again and again, and it infinitely would descend, like the numbers are spiraling, and that means that you couldn't find whole number solutions for n equals 4. So Euler used infinite descent and also imaginary numbers, which is the root of -1, to prove n equals 3. So yeah, that proved n equals 3 and n equals 4. It proved Fermat's theorem for those, and also it would prove Fermat's theorem for any multiples of 4. So like, for example, 256 can be written as 2 to the power of 8 and also 4 to the power of 4. So it would prove Fermat's theorem for any multiples of 4 and multiples of 3. So essentially, like, all that was left was finding proof for the prime numbers. And in 1776, Sophie Germain, she was born in France, and she made a great contribution to Fermat's theorem, despite being a woman, because it was very frowned upon, and like the odds were all against her. Like, she wouldn't get accepted into like academies, even though she was like a genius. So she did take like a male pseudonym and studied at an academy, and she did like such great work. She found so she found this new type of prime numbers, which it's 2p plus 1, where p is prime, and basically she said that Fermat's theorem wouldn't work, so there would be no solutions if n was to equal this special prime number called the Germain prime after her, and because the restrictions on the theorem would be too small. So
Do you want to share with the class?
Drake's equation.
Wait, what's wrong with that?
Isn't that very awesome? It's Drake. The singer Drake.
Why are you thinking about episode 1? Guys, go watch the first episode. But
It's about how we were laughing last time.
But why do you think of a Drake's equation?
Because he laughed at Drake's equation.
Drake's equation was funny. So yeah. So Fermat's theorem had been proved for like some special cases, such as like multiples of 3 or 4, some prime numbers. But like still it wasn't proved for every number. And then there were more mathematicians found proofs for like n equals regular primes and 5 and 7 and so on. And then in the 20th century, computers let people find proof for Fermat's theorem to like a billion, but it was never infinity. So I'm gonna start to talk about Andrew Wiles, who is he's the amazing mathematician who found the proof. So when he was 10 years old, he was in a library and he found E.T. Bell's book on maths, and he found Fermat's theorem, and he said it looked so simple, yet all the mathematicians of history couldn't solve it. And it is. The thing about Fermat's theorem is that it looks so easy. It looks like Pythagoras, and you'd think, oh, that's easy. You can understand that. A 10-year-old can understand it, but no one could solve it. And so he decided then, when he was 10 years old, that he would spend his life trying to solve it. So yeah, in 1975, he began studying at Cambridge. His professor told him to study something else instead of Fermat's theorem because it kind of seems impossible. So he studied elliptic curves, which he didn't know, but it would be really closely linked to the solutions for Fermat's theorem. So elliptic curves are I'm not gonna go into so much depth because it's a really confusing thing, but they are cubic curves that have the form y squared equals x cubed plus ax plus b. And yeah, they were made up of you can say the sort of DNA for elliptic curves was it was called the L series, and it was just a bunch of numbers that were kind of the thumbprint of elliptic curves. And the thing about elliptic curves is that it was really hard to solve to find a solution for it because there could be infinite solutions. And then in around this time in Japan, there was these two guys, Taniyama and Shimura, who studied modular forms. And that's also like the book I was reading, Fermat's Theorem by Simon Singh. If you're interested, you should read it. Yeah, it's a great book. So it calls modular forms entities. I don't really know how to explain it because they're so beyond our understanding, kind of. So modular forms, they're symmetrical. They have two complex planes. So each has an imaginary axis and a real axis, and it's in hyperbolic space, which I spoke about in the last episode.
Oh, now I'm good.
Yeah, kind of, but a fourth dimensional on. Yeah. And Taniyama and Shimura made a conjecture, which was that modular forms are elliptic curves in disguises. So that was just a conjecture. They didn't prove it, but they were saying because basically the DNA of both, the numbers, the L series I was talking about, it's the same between modular curves and between modular forms and elliptic curves. It's the same. So that's kind of difficult to comprehend, but basically it's setting the path for the proof of Fermat's theorem because in 1985 Gerhard Frey, sorry if I'm mispronouncing that,
Is it still alive?
yeah, pretty sure.
Yeah, he's
Sorry.
probably watching this video, so sorry for that.
Sorry, bro. So he conjectured that, well, basically he thought if Fermat's, so let's say that there was a solution to a to the power of n plus b to the power of n equals c to the power of n for n greater than 2. If there was a solution to that, it created this weird elliptic curve that was not in modular form. So that meant that if there was a solution to Fermat's equation, then the Taniyama-Shimura conjecture would be wrong. So all that means is, once his conjecture was confirmed, this meant that to prove that Fermat's last theorem was true, all you needed to do was prove the Taniyama-Shimura conjecture, which was proving that elliptic curves are the same as modular form. So that's all that Andrew Wiles had to do, and once that conjecture had been confirmed, and he found out all he had to do was just prove the link between elliptic curves and modular form. All he had to do was prove that, and after 7 years, Wiles found a way to prove Fermat's last theorem by proving that elliptic curves were modular forms. So, just to clarify, I'm pretty sure, don't quote me on this, but modular forms are basically like hyperbolic fourth-dimensional graphs, and elliptic curves, so those are graphs with like the equation y squared equals x cubed plus ax plus b. If you put it into decimals, you get like that. That's what it looks
Sideways.
Yeah, that's what it looks like if you put it into decimals. I don't
it's
know.
a one-to-many function.
Shut up. So yeah, and whilst in 1993 he gave a lecture in Cambridge that explained his proof, and that was it. He like had his name in mathematical history, and he was in like newspapers, and he was like a hero of mathematics. But when he was getting it checked, so this was like when he was getting his proof checked by a professor, he did find like a mistake, which is like, that's like life changing. He was so close to success, and there was a mistake, but he did fix it like a year after, so it's fine. And yeah, he made his place in history as one of the greatest mathematicians to ever live. And yeah, to quote the great Andrew Wiles, I think I'll stop here.
So, my topic is how cells talk to each other, but I'm going to put it into a context of a relationship to make it easier to understand. So, imagine you're in a relationship. You and your partner need to stay in touch to keep everything running smoothly. Communication is key. So, like that, cells in your body need to communicate with each other. So, the cells are like people in this scenario, and they've got their own version of like texting, calling, to like make sure everything runs smoothly. There's no problems, everything is fine. Okay. So, why do cells need to communicate? Just like in every good relationship, communication is key. Again. So they need to make sure that everything in the body runs smoothly. So they need to tell each other when it's time to divide, or when it's time to grow, or when it's time to like break up. So when they need to die. So
That's a very like extreme way to break up with someone. Just die.
that's the only way I can think of like making it relate to the relationship scenario. I mean, like if they're dead, they're not part of the relationship anymore.
Wait, you're forgetting you're dying, killing the old part of yourself.
Yes.
Yeah. Okay.
Or it can be used to like check if there's an infection.
The breakup.
Oh no, a different point. Why they need to communicate.
Oh right.
So like if a pathogen comes in and all the white blood cells they're like, oh, there's a foreign body, we need to start attacking that, but they need to communicate it so they can actually like figure out where the pathogen is, and they all just go towards their kill it. Okay, now we're on about like the signals, so how they like text or call or communicate with each other. So they do this by sending chemical signals like hormones, proteins, or neurotransmitters. So when one cell needs something, they just send out the signal to like every other cells in the body, and the right one responds. And then you have the receptors. So it's like when you're texting your partner, you would want to make sure that like you send the text to the partner, like they're the ones receiving it. You don't want to like wrongly text someone like a message. Yeah. So it's like that's where like the receptor part comes in. So like imagine like a receptor being like the right person to text. So they're like proteins on the cell surface that unlock the message once the signal comes in. So if the signal fits, then the receptor reacts. So it's like the message gets opened and your partner's like, yep, I've got the message. And then once the cell gets the signal, it's like a whole mess. It's like, say you text your partner, let's go on like a date night, and then like that one text, you get like thousands of different ideas, like, oh my god, movies, restaurant, that sort of stuff. So like that, the cell response is called like signal transduction. So it's kind of like a small message is being received, and that leads to like a massive chain reaction in the cell. So it could either start dividing, it can produce proteins, it can even pack up or like move to a completely different part of the body. Yeah. And then there's types of communication. Cells communicate in different ways. So we have autocrine communication, which is like texting yourself. So some cells are like so self-sufficient that they just need to give themselves like a little boost. And they send signals towards their own receptors like, oh yeah, I need to do this now. I just need to remind myself.
Wait. So in what case would a cell have to do that?
It's to do with like, you know, like insulin cells when they start producing like a bit less insulin, and they just like, not like realizing in like a human way, but they're just like, oh, there's a change, now I've got to produce more insulin to like counteract that change.
But isn't that's done by a whole system in the body though? Like that requires more hormones and other parts of the body to do it.
But
Like
they
it's not
all
just the
work
cell.
together. Like you work with yourself, but you're also part of a bigger network that works with you at the same time.
Wait, so what is that regulator that tells if insulin's high or low? What's it called? AGT?
I don't remember.
Whatever it is, but doesn't that tell the insulin cells that the blood level is low?
Yeah, but then it sort of needs to like, you know, like a pep talk type of thing.
Right.
Like yeah, it gets like they tell it to do that, but
Okay.
then they've also got to like process it by
Okay,
themselves.
yeah, right. That makes sense, yeah. Okay, thank you.
Then you have the paracrine communication, which is like talking to a friend next door. So it's like the cell sends a signal to like nearby cells like really fast. So this would be like, you know, like phagocytes, when they detect like a pathogen, they need to like, it's not usually one phagocyte that like engulfs the pathogen. You usually like, you need to alert everyone near you, and then you all go and attack that one pathogen at the same time. And then you have endocrine communication, which is like long distance relationship. So it's like hormones are sent out via the bloodstream to like distant cells. So it's like, imagine they're living in like another country type of thing. It's a slower response, but it gets towards the whole body. And this is stuff like adrenaline. And then there is direct contact, which is just cells just need to get really, really close and just communicate. and that's like immune cells. They always like, again, not in the context of like human wise, but like they always like gather together and be like, oh, is everything okay? Is everything okay? Did you see the new pathogen? Blah blah blah. Do we need to go and attack? Like a little like private,
Gossiping.
yeah, like a private chit chat type of thing. So that's all.
Oh, with the cells.
So that's all the ways cells communicate with themselves. Now we're going to talk about what happens when communication fails. So you could consider this as like relationship trauma. So you've got like 3 different examples I'm going to like talk about. So first you've got cancer. And this is like if you send a text to your partner and they just keep ignoring it. So it's like, you know, when cancer is just uncontrollable cell growth. So it's like other cells recognize this and they're just like, you need to stop like dividing, but the cancer cells just, yeah. But the cancer cells just ignore it. They just don't care. They just keep dividing out of control. That's one example. Next, you have diabetes, which is also similar to cancer, like in the way that they ignore cell messages. Like, so they just keep ignoring messages, and like sugar builds up, diabetes, similar to like the cancer cell type of way. And then you have autoimmune diseases, which is a bit different. And this is like a partner getting too possessive, where it like starts attacking you instead of protecting you.
Maybe we are here to demonstrate that.
So it's when like the immune system, like I don't know what it is, they just undergo like a change and they just start attacking your own body cells because they just misread the signals. So they just start getting like over possessive and they're just like, you're wrong, you're wrong, you're wrong.
Miscommunication trope.
Yeah, so
Miscommunication trope.
but like to the extreme. So that's about it. So your cells are constantly in relationships with each other, sending messages, making plans, even some drama. Just like human relationships, communication is everything. That's it.
Thank you, Aldona.
So yeah, that's all of the we had to say today, or we had to say for today. But we hope you guys enjoyed it, and
Subscribe, like this video,
Smash that like button.
your face.
and follow us on LinkedIn.
Oh yeah, we'll keep this updated on LinkedIn.
We'll keep this updated on LinkedIn. But yeah, that's about it. We shall see you next time.
Yeah, hope you guys enjoyed this. Bye.
Bye.
Okay.